Okay. Good evening, everyone, and thanks a lot, Ignacio, for the amazing introduction and for the invitation. And it's really nice to be here, especially it was a really beautiful day today. And I want to talk, what I want to talk to you about today is really sort of my story of what quantum computation is about and why it's so interesting. I think it's an amazingly fascinating field, and I want to tell you my angle. So what you see here, I am both professor at the Hebrew University, and I'm also the chief scientist and the co-founder of QEDMA Quantum Computing, and that's a company that attempts to handle noise in quantum computers, and this is us when we were very young, 3 years ago, and now we are 3 times larger. Okay, so am I doing it right? Yeah. Okay. So quantum computation at 1994 started with, it started before that, but at 1994 was sort of an earthquake in quantum computation with the discovery of Shor's algorithm. I'll tell you more about it later, but it's an amazing quantum algorithm that made everyone know about quantum computation. And then came also results that told that actually quantum computation can be performed in the presence of noise, meaning it is a realistic model. But at that time, there was something like a few dozens of people that ever knew about, that even heard about quantum computation. Now, fast forwarding to 2035, or rather to now predicting to 2035, this is McKinsey report of the value at stake in applications of quantum computation in 2035. And that's $700 billion. So what happened between then and now to the point that actually now people, it's hard to get around without hearing about quantum computation, even in comics or in jokes or in everyday life. What happened? So over the time between then and now, there have been tens of startups and major technological giants that are attempting to build quantum computers. And really what I want to tell you about is why there is so much interest in this. Why is it so exciting? Okay, so I think there are 3 main reasons to that, and they're all sort of combined together. The first reason is the conceptual depth of the field. It's actually somehow really diving very deeply into the question of what nature can compute. And this marriage between computer science and physics somehow provides very deep insights, both to physics, to computer science, to technological aspects of everything around us. It's really ubiquitous in its depth. Okay, so that's one thing. The second thing is the scientific impact. It's really remarkably beautiful in how the model is really beautiful. It's mind-boggling. It's profoundly deep, and it touches on very beautiful new mathematical and physical problems. And it has a huge impact on physics and science. Okay, so that's 2. And 3 is, of course, the technological potential. There is really very promising technological potential in this area. We are still probably only touching, we're only seeing the tip of the iceberg of where it can go. And already now it's really exciting of where it can actually go. And it's so exciting that maybe it deserves a full slide. And the full slide, again, is really limited in its vision. We probably will see many, many more applications in the future. But already now, we think that there will be really profound effects, profound applications, very important applications on discovery of new drugs, discovery of new materials related to fertilizer production and batteries, and financial services There will be optimization abilities that would help in that direction, logistics, sustainable energy, and more. And the truth is, we really don't know where it will go. Now, it's so exciting that people tend to exaggerate a little bit, and I don't really know. I mean, there's obviously a lot of hype, but if you look underneath the hype, it's still true that there may be really remarkable implications related to sustainability due to quantum computation. It's just that maybe the certainty with which people say it is too much, but it could really be dramatic. Okay, so just to tone down a little bit the hype, we know that it might be extremely exciting, but we also know that it's not going to solve all our problems. It's not as if that you take a problem and then with a quantum computer we just can solve it. That's not the case. The problems that are solvable by quantum computers are very they need to have a limited structure, and in fact, right now we have few problems that we can solve dramatically efficiently, exponentially faster than classical. But most problems we don't see advantage. For those problems in which we do see advantage, the advantage is very dramatic, and those problems, for example, simulations of physical systems and everything that's related to that, we know that there will be exponential advantages there, and the implications are really mind-boggling in terms of what we might be able to do with simulating physical systems and chemical systems with using quantum computers, which is really natural for them. So they will be able to do it, unlike what we can do today. Okay, so now with all this potential, we have to also remember where we are now. For now, we don't have quantum computers that can do all these things. What we have are quantum computers of sizes which are between a few tens to a few hundreds, and they can run quantum algorithms of roughly, say, hundreds to thousands of gates. I'm being here optimistic. Now, in order to actually perform all these potential applications, we need to actually run at least 2 orders of magnitude or 3 orders of magnitude larger algorithms. And we are far from that point in time. It might take a few years. It might take 10 years. We don't really know. Okay? However, there's been amazing progress on hardware, really remarkable progress on hardware in the past few years, in the past year especially. And I think that it's very fair to say that at this point, 2 years ago, I wouldn't have said this with such confidence, but now, myself, I'm confident that it will happen from the point of view of hardware. And what will be the applications? This is a very big question. Okay, so I want to start at the basics. I want to tell you a little bit about quantum computers and why and what they are, what's the model, what are the ideas that underlie quantum algorithms, what are the main challenges or what is the main challenge, which is noise, and where we go from here. Okay, and I want to start from scratch. What is computation? How many of you have been in Barcelona? Okay, a good deal. So this is a very, very famous building. You can't miss it when you're in Barcelona. It's this beautiful La Sagrada Familia designed by Gaudi more than 100 years ago. Gaudi didn't have computers, even not classical computers, but he needed to compute. So he wanted to design this amazing construction with arcs sitting one on top of the other. Without a computer, how would he solve the equations that would lead to an equilibrium, to a stable construction? So what did he do? He had a very, very clever idea that if you had the chance to actually go beneath the Sagrada Familia to the basement, you would have seen his construction. what he did is he took ropes of length proportional to the arcs that he wanted to build, and he tied them one to another at the locations where he wanted the arcs to lean on each other. And so he had this entire construction, and then he took this construction at the edges and hang it to the ceiling. And then gravity immediately performed the calculation, the computation, and found the equilibrium. And this is a very, very beautiful example of a computation. And actually in the basement, you can see a mirror underneath this rope construction so that you can actually see how the shape is in the, right side up. Okay, so this is a computation, but this is not the kind of computation that we are looking for. We don't want to go and tie ropes to each other in order to solve various questions. This is not what we call universal computation. So universal computation is a model for computation that can perform can solve any solvable problem. And here is Alan Turing, who invented a model of universal computation that's called the Turing machine, which is basically a tape and a head that goes around and reads and writes the letters. And it turns out that and it's governed by some kind of local rules. Every time the head just sees a letter, and the state of the finite state machine here, it just decides if to go right or left and what to do with the letter that it sees. So it's just a local step, very simple. But it turns out that this accumulation of this local step one after the other creates as complex evolution as you want. It's universal. It can basically simulate any or perform any computation that you can think of. Okay, but this is not the only model of computation that you can think of. You can also define DNA-based computation with local rules of how the DNA molecules, atoms sort of connect. And there are also other models like this is the game of life, the famous game of life, in which you start with some configuration of the whole lattice, and then the configuration in each pixel, there is either black or white, and then the next configuration depends on the previous one by some local steps, okay? Just for example, if the pixel is black and there are only 3 white neighbors, then the next step, it's also black, something like that. And it turns out that this leads to really remarkable complexities. I really recommend that you go into the web and search for the game of life. It's really beautiful. Any complexity can be derived from this because this is a universal model. And it turns out, and this is a very important thing, that all these models that seem very different are in fact very similar. They're similar in the sense that they're local. They evolve in time by local rules, which are very simple, and these simple local rules just accumulate to give the complexity of a universal computation. As complex as life. This is why John Conway, who invented it, called it the game of life. So the point is that these models are somehow related to each other in the sense that they have the same logic of local update rules. And it turns out that they can actually simulate one another without too much overhead. Meaning, if there is some evolution going on in, say, a DNA computation, the Turing machine can simulate it, where if the original computation took n steps, then maybe the Turing machine would take n squared steps, but not much more. Okay? And there is a very important thesis that's called the extended Turing thesis, which stands at the basic of theoretical computer science, essentially. And it says that no matter what model we're using, a function or a problem is going to be to have the same difficulty as in a different model, in a different classical model, because the logic of information propagation or information processing is more or less the same. So the thesis says any physically realizable computational model can be simulated efficiently with only polynomial overhead, meaning n goes to n squared or n to the n to the 3, by a classical Turing machine. And this is really important because basically it says, if I want to understand how difficult a problem is, it's enough for me to study how its solution will scale with the size of the problem, whether it will be n or n squared, etc., or exponential. It will be enough for me to decide about this by just looking at Turing machines. I don't have to go to all the different models of computation. Okay, so it's a robust notion how difficult the problem is, whether it will take me a polynomial number of steps to solve or an exponential number of steps to solve. This question doesn't really depend on the model. It may depend whether it's n or n squared, but not whether it's exponential or polynomial. Okay? So this is the basis for theoretical computer science before quantum computation enters the picture. Because it says the question of whether functions and problems are hard or easy, exponential or polynomial, is a robust question. It doesn't really depend on the nitty-gritty details. Enter Feynman, who says, quantum many-body systems seem to violate this thesis, as we do not know how to simulate quantum many-body systems using classical Turing machines or classical computers with only polynomial overhead or efficiently. We do not know how to do that. As far as we know, it requires exponential time. Okay, what does it say? Well, if you take this and try to go one step further, what basically Feynman said is, if you have a quantum computer, meaning if you have a computer that's based on quantum mechanics, this computer will be stronger because it cannot be simulated efficiently by classical computers, meaning it does something difficult, it does something interesting. Okay, so could computers building on quantum mechanics be exponentially better? Now, okay, so this was the point where quantum computation started, and there came a step where, which is a very important step in science, of separation between different parts of the problem. One problem is how to build a quantum computer, and the other problem is what's the model? What are the principles? What are the principles underlying quantum computation? And this abstraction step was done by Deutsch. This is a very important step, and he defined what a quantum computer is mathematically. And the question is of how to implement this quantum computer to realize it in the lab is a different matter, and he left this to experimentalists. And so all these suggestions for does this do anything? Yes. So all these suggestions for different implementations doesn't really change the fact that the model itself will be described by a quantum circuit, which I'll describe to you in a second. And this conversation between computer science, the computer science part of the equation, and the physicist part of the equation, meaning the computer science angle on quantum computers, asking what's the model and what are the algorithms, etc., and the physics questions, which are about implementation, etc. This interaction between the two is an extremely fruitful interaction that has been going on for ever since quantum computers were invented, and it's really beautiful how the two fields evolved because of this interaction. Okay. So I want to start basically by explaining what is the model of quantum computation, and then a little bit about quantum algorithms. And I'm actually going to be as ambitious as showing you your first quantum algorithm. It's going to be very simple and painless, I guarantee. And then I'm going to tell you about the challenge, the noise. Okay, so let's start again from the basic point of the most elementary unit of a quantum computer. That's a qubit, a quantum bit. What's a quantum bit? Well, basically, the first principle in order to define a quantum bit is the superposition principle. The superposition principle says that a quantum system can be in a superposition, in a linear combination, or in some combination of all its possible classical states. So forgive my miserable attempt to draw a cat here, which is both dead and alive, but this is it. And you can think also of a door that's both open and closed, or a spin that's pointing up and down. It doesn't really matter. A qubit is anything that is capable of exhibiting being in some combination of such two states which seem not related. And this combination is described mathematically by a vector, two-dimensional vector with complex coefficients. And this vector can be thought of as pointing in one direction in space. Okay, that's the Bloch's field, and this vector points in some direction. Okay, so that's the first principle, the superposition principle, which gives us the qubit. And now in order to, once we have a qubit, we want to measure it, we want to extract some information about it. And the quantum measurement principle is something that's really mind-boggling, as I'm sure you've heard about. And it basically says that there is no deterministic answer. If you measure a qubit, you get a probabilistic answer. If the state of the qubit is, say, a combination of 0 and 1, then it will be measured to 0 with some probability depending on the coefficient in front of 0, and it will be measured to 1 with this probability. And once you measure it, it collapses. It changes. And so there is a classical outcome, 0 or 1, plus the state projects onto the answer that we got, onto either 0 or 1. Okay, now this thing is obviously something that is really mind-boggling of how do you actually explain the fact that we don't know what will be the answer. There's nothing in the system that tells us what the answer will be, and that the measurement affects the result, the measurement actually affects the system and changes it. And all these was a bit too much for Einstein, and I'm sure you've seen this picture. Einstein worked a lot to try to change and to find other explanations, and so far we think he was wrong. Okay, so these are the two principles on which we base quantum computation. Now, okay, so before we build a quantum computer made of many qubits, let's just see what we can do with a single qubit. So what can we do? Already with a single qubit, there are some interesting things to be done. I talked about how you measure a qubit. Now the next thing that's interesting to do is to make it evolve in time. So the evolution of a qubit is governed by what's called Schrödinger's equation. And basically it tells us that the state of the qubit, that's the vector, rotates rigidly in space. The rigid rotation is determined by a unitary transformation, meaning it's a rigid rotation. So such a single qubit will rotate by in some amount, and we call it a quantum gate, the thing that rotates it, the operator. And there are various quantum gates, the NOT gate, the Hadamard gate. The NOT gate is basically corresponding to a flip of the bit. 0 goes to 1, 1 goes to 0. But the Hadamard gate takes us from 0 to a superposition of 0 and 1, and from 1 to a superposition of 0 and 1. So that's a quantum gate. That's a seriously quantum gate. But you can also think of rotations and other angles. Okay? So that's how we should think of single qubit gates. And again, already here, there's something interesting with a single qubit gate, and that's interference. Okay, so think of the Hadamard gate. The Hadamard gate starts from a 0 and creates a state of 0 plus 1. And it starts from a 1, creates a state of 0 minus 1. And if you measure it, as I told you before, the answer will be probabilistic, with probability half 0, with probability half 1. So it's like a quantum version of a coin flip. Now, the interesting thing is that it doesn't behave exactly like a coin flip. It behaves a little bit like a coin flip and a little bit like something completely different. If you start from the state 0 and you apply the Hadamard gate, you get this superposition. And if you now measure, you get a random bit. But if you don't measure and you apply again this quantum flip, well, if you had applied again a classical flip, then you would have gotten again a random bit. But in quantum world, things are different. If you apply again a quantum flip, what happens is that by linearity of quantum mechanics, this 0 goes to 0 plus 1. This 1 goes to 0 minus 1. And things cancel. And therefore, what you get is, in fact, a deterministic answer, 0. And this phenomena is so interesting that it has many different descriptions. The first description is that this is similar to interference of waves in water that can cancel each other. The plus half one and the minus one, the minus half cancel each other and leave only the 0. There's also the description of path in the space that's called the Hilbert space of the possibilities of the configurations of the quantum state. So you start from 0 and 1, and then you apply the Hadamard. 0 gives a little bit of weight, or half a weight to 0, and half weight to 1. And then you apply again the Hadamard, and each one of the members in the superposition gives its own weights, but the arrows here can have different signs. And this is why the weight of 1 at the end, which is the weight of this path plus the weight of this path, is going to cancel out, because the weight of this path is going to be positive, and the weight of this path is going to be negative, and they cancel each other. And it's this interference pattern, the ability to cancel, which basically makes the power of quantum computation so strong, because if you now take this and make this into exponentially many paths that talk to each other, you can actually design a quantum algorithm that essentially, if you do it very cleverly like Shor did, essentially all the paths that lead to bad answers or outcomes that we don't want cancel, whereas all the paths that lead to good answers, they build up. And then at the end of the computation, we will only measure results that we wanted. So exponentially many paths talk to each other in this evolution, in this quantum evolution. And this is the strength underlying a quantum algorithm. Okay? So I think we are now ready. I don't know, are you? To our, well, actually I thought that we're now ready for our first quantum algorithm, but before that we have to understand how to build up to a quantum algorithm by adding more qubits. So when you add more qubits, something else enters the picture, and this is the exponentiality. So interference already appears with a single qubit, but now when you add more qubits, we get this exponentially many path. So why is that? Well, if you recall the superposition principle, it says that a quantum system can be in a superposition of all its possible classical configurations. If you think of 1 bit, it has 2 possible classical configurations. If you think of 2 bits or 2 spins, it has 4 possible classical configurations. Every bit that we add multiplies the number of configurations by a factor of 2. So if after 500 bits, we already are at a space which is of the size of 2 to the 500, which is more than the number of particles in the universe estimated. Okay? So very small quantum systems are described by huge Hilbert spaces, exponential in size. And so the space that describes this, of putting together qubit by qubit, basically creates the ability to describe states which are superpositions of exponentially many possible configurations. These strings of bits 0000, 0001, these 2 to the n possibilities, there are exponentially many of them, and so a state of a quantum system of n quantum bits requires exponentially many coefficients to describe. It lives in a Hilbert space of exponential size. Okay, and this difference between classical bits described by n classical bits, whereas n quantum bits described by 2 to the n complex numbers, is what gives quantum computation its power, together with the ability to do interference. And it's this difference that made the Feynman look at it and say what I said earlier, that there should be amazing power in quantum systems if we harness them as quantum computers. Okay. Now, I wanna mention one point that is something that we've been hearing all around, which is entanglement. So in quantum bits, described by this state of a superposition over 2 to the n possible configurations, well, these this very complicated state, in order to describe it, it's not enough to describe the state of each single qubit on its own. Most of the information about this state lies in the correlations between the bits. If you just needed to describe each qubit on its own, then the description would have been very small. But to describe the correlations, this is what sort of the secret that is really hard to describe. It requires exponential description, and it's these correlations that are called quantum correlations or entanglement that makes these systems so mind-boggling and so hard to get intuition about. Okay, so these are the multipological entanglement, and now we want to start manipulating them in order to get algorithms, as I promised. So let's think of an initial state like this, where the first qubit is initialized to the state 0, and second to 1, etc. Now you want to start manipulating them. So you can apply these single qubit quantum gates, say NOT and Hadamard or rotations. But this is not enough, because what will happen is that each qubit will sort of play on its own and they will not be entangled. So in order to actually create something interesting, create these highly complex quantum states, you need 2 qubit gates. You need gates that create correlations. And for example, and don't worry about the matrices if you don't know what they mean, it's a quantum operation that basically makes 2 qubits talk to each other. And in order to create a quantum algorithm, you basically put these operations one on top of each other, and this is what, if you choose your basic operations correctly, for example, you allow all 1 qubit rotations and you allow this C0 gate, then what you will be able to do is you will be able to create any quantum state that you want if you put sufficiently many quantum operations. Okay, so I think now we're ready to define quantum algorithms. What are quantum algorithms? I've actually already defined them. They're just concatenations of these small steps, just like in Turing machines or in the game of life, where you concatenate small steps, elementary steps, and the complexity is built out of this. Here too, you want small rotations, single qubit rotations, 2 qubit rotations, and you put them one on top of the other, and you create these complexity. But now these states rotate in an exponential dimension, okay? In this exponential Hilbert space, and you get this quantum complexity. Okay, so here is a quantum circuit. Your input is this state, for example, just a classical configuration, not yet any superposition. You evolve by this dynamics of single or 2 qubit gates, and you measure at the end, and you ask, and your complexity, or you measure how, sorry, not measure, but you estimate how complicated your algorithm was and how fast it was by basically counting the number of elementary steps. Okay? So that's a quantum algorithm. A quantum algorithm is the sequence of elementary steps, and we know whether it's fast or slow according to the number of elementary steps. Okay, so now let's go to what I promised and do some real stuff of quantum algorithms. And in order to design a fast or an efficient quantum algorithm, I want this number of elementary steps to not grow too fast, to scale like with the size of the system, like n or n squared polynomial, but not exponential. this is when I will say that the algorithm is really efficient. Okay, so in order to design new quantum algorithms, let's first do something which is, I want to start again in a basic place. Let's first make sure that we can do at least what classical computers can do. If we're going to work with quantum computers, we want to know that at least they are as strong as classical computers. Okay, so that's true. We can relax on this front. It turns out that classical computation can be performed by quantum computation, essentially because, for example, I showed you a NOT gate, and it turns out that other classical gates can also be done quantumly. The only caveat in quantum is that things need to be reversible, because as I told you, it's a rigid rotation. But also classical computation, even though it can be non-reversible, it can forget, it can also not forget. I mean, it has the privilege of writing down the information and then it doesn't forget. And then it can be performed quantumly. So anything classical, anything that can be performed by a classical computer can also be performed by essentially the same number of steps on a quantum computer. But this is not why we're here, right? We want something more. So what more? As I told you, linearity is going to come into play. And linearity is going to imply exponential parallelism. Why is that? So think of this Hadamard gate that I told you about before. 0 goes to 0 plus 1, 1 goes to 0 minus 1, which basically means that if we start with 0, 0, 0, we get very quickly, with n gates, a superposition over all possible inputs to a certain function. And now, if I know that I can compute a given function classically, I told you I can compute it quantumly, but by linearity, if I get as input a superposition over exponentially many inputs, I can also compute the function on those exponentially many inputs in parallel, because by linearity, if I compute it on this register, it just computes it on all of the inputs at the same time. So you get exponential parallelism just by linearity of quantum mechanics. This seems like too good to be true, right? I mean, it seems like we have a function, we can compute it with the same number of gates as classical, but now we apply it on exponentially many inputs, and lo and behold, we get exponentially many outputs. But the thing is that now if we measure this output, we try to find the answer for exponentially many questions, the thing will collapse and we lose immediately all this exponentiality, and we get one input and one output, and all the magic goes away. So where do we gain? Okay, so remember the interference pattern I told you about? This is where we gain. Here, we didn't actually try to make the different inputs talk to each other. But if we do try, and we try to use interference, and we design the interference cleverly so that different paths will talk to each other, then we get access to this exponential size of the Hilbert space, or the exponential power of quantum computation. So now we're ready. This is the first quantum algorithm, and hopefully it will be short and sweet. It was designed by Deutsch already in 1985, and it tries to solve the following problem. You're given a function, f, and it's a very simple function. It takes a bit, 0 or 1, and it outputs a bit, 0, 1, or 1. And we basically want to understand something very simple about this function. It's either constant, meaning no matter what the bit is, it gives the same answer, or it gives two different answers. That's what we want to understand. Classically, what would we need to do in order to understand this? How many times would we need to evaluate the function? Twice, because there are two inputs, 0 and 1, and if we know the answer f of 0 and f of 1, we know whether they're the same or different. So 2 times. But quantumly, it turns out that we can do better using this Hadamard gate. So let's see. That's it. That's the algorithm. And let me explain it. You start from a state 0, and you add a helpful qubit in the state 1. And you apply the Hadamard on both qubits. So this, if you remember, creates a superposition over the first qubit being in the state 0 plus 1. And this guy is going to be in the qubit 0 minus 1. But think of this qubit, it's now in a superposition over the two inputs. And now you apply the calculation of f, the computation of f, in superposition over these two inputs. Now, if you just measured now, you would have collapsed, like I described before. But instead of measuring, we can now do something clever and apply this Hadamard. And this Hadamard essentially makes the two paths talk to each other and either constructively interfere or destructively interfere. And then it turns out that when you measure here, you'll get the answer. 0 if they're the same and 1 if they're not. Okay? So somehow the Hadamard makes the two talk to each other, the two different paths, using interference. What happened here is we just evaluated the function f once and not twice. So we saved something very small. We saved one evaluation. Instead of 2, just 1. But, from at least my experience in science is that it always starts with a very, very small step. It always starts with something that seems like unimportant, but there is something there that's mind-boggling, that's not easily understood. And this saving of one evaluation of f instead of 2, going to 1, this thing actually led to the famous Shor's algorithm. So it's basically this algorithm that I've just went with you through. You won't believe it, but it's this algorithm, basically just slightly improved, but really the same quantum circuit that actually leads to Shor's algorithm for factoring numbers, which is a problem that's notoriously hard, and essentially all the important crypto systems rely on its hardness. So how did this happen? Well, in a sequence of events, in a sequence of sort of improvements of this Deutsch algorithm, from this algorithm that you just saw, essentially the same idea going to more qubits, and the same idea going to a slightly different problem, but the circuit is the same. Simon, who actually refuses to put any picture of his on the web, talked with Bernstein Vazirani, who came up with this algorithm and came up with a slightly different algorithm, but again, the same circuit looks exactly the same. And Shor, who said in the talk of Simon, came up with the idea that with the same circuit again, he can actually, but working on a slightly different input, he can actually, and using, instead of Hadamard, something slightly different to create this interference, he can actually solve the factoring problem. So to me, this is a very inspiring story of starting from something very simple and expanding it to really sort of something very big. Okay. How am I doing in time? Yeah. 15 minutes or how long? Something like that. Okay. So, let me very quickly skim through the idea of Shor's algorithm. Shor's algorithm is the algorithm of to solve the following problem. Maybe this is slightly technical, so it's basically oriented to the audience with slightly more technical background. But I'll spend on it something like 1 minute. So Shor's algorithm is perhaps the most famous quantum algorithm. And what it does is it's given an input number n, and it wants to find the factors, the prime factors of n. And it turns out, in a not so interesting argument, which I won't go into, that in order to do that, it's sufficient to find the period of some function, y to the r. So y is some number which is co-prime with n, and it's sufficient to look at y squared, y to the 3, y to the 4th, and find the periodicity of that. Okay? And so here is Shor's algorithm. You first generate all inputs using the Hadamard gates like we did before. This is the superposition over all inputs A. And then you evaluate the function f on this input A, where f is this function y to the sum to the A, which we want to find the period of. Okay. And then once you measure the result, this collapses the first register to a superposition with this periodicity that we're trying to find, but shifted. Now, if we just measure it, we won't see anything because of the collapse. We have to somehow be clever and connect and somehow make all these different members in the superposition talk to each other so that this periodicity will be discovered. And the way this is done is by what's called the Fourier transform, which is a variant of the Hadamard gate, but for what's called larger groups. And with this Fourier transform that quantum computation can perform, what is revealed is that from this periodic superposition, one gets a superposition whose weight is concentrated on harmonics of R, 1 over R, 2 over R, 3 over R, and then the state can be measured and R can be extracted. Okay, so that's the essence of Shor's algorithm, and the interference patterns that I told you about happen between this point and this point. All these points talk to each other, all these members in the superposition talk to each other to allow this calculation of the periodicity through the Fourier transform. Okay, so this leads to really this remarkable discovery of exponential quantum advantage. I think at the point when this was discovered, people didn't really understand this, not only understand, didn't believe it. And the explanation was, well, yeah, this is a model that can perform exponentially better algorithms, but it must be impossible to realize it physically because it's too good to be true, essentially. But also because there have been other models which are also capable of performing exponentially better algorithms or solutions to various problems, but they rely on too strong assumptions like infinite precision or things like that, infinite energy. So people were thinking maybe there is something underlying, something fishy in this model. Okay. So before I go to this point and try to see if this is a realistic model or not, let's see what else it can do except for factoring. Factoring is an extremely important problem because it basically cracks very important crypto system called RSA. But there are other various quantum algorithms that can be done using this idea of interference and also somewhat different ideas. I won't go into explaining to you those algorithms, but just to give you a taste of what can be done, one of the suggestions is to speed up the solution of linear equations using somewhat similar ideas like Shor's algorithm. That's called phase estimation, and then a very a direction which really excites people nowadays is variational quantum algorithms, which is sort of a similar thing to machine learning in quantum computation, where basically one tries to generate quantum states using a quantum circuit, which in itself is something that we learn during the algorithm. The quantum circuit itself depends on some parameters, and we update these parameters based on some feedback of optimization of some function that we are trying to optimize, for example, the energy of the state with respect to some physical system, to some Hamiltonian. So this is another family of algorithms that people are very hopeful, or some people are very hopeful that it will lead to very interesting and important applications, such as finding states of minimal energy of various physical systems. And then perhaps the most important applications for near-term quantum computers is that of simulating quantum systems. And this sort of closes the cycle, because Feynman suggested quantum computation because he was motivated by the fact that it's hard to simulate quantum systems, many-body quantum systems by classical computers. Quantum computers are going to be exactly, they're tailored for this task. And this is true. Quantum computers are capable of simulating many-body quantum systems efficiently, because the structure is really aimed for that. Okay, so this is sort of some glance at what can be done, and I have to say, just to be just so that that the situation. The number of quantum algorithms is not very large. I've basically put here most of the families of quantum algorithms that people are thinking of. And I really believe that we've only seen the tip of the iceberg. In fact, I believe that perhaps this is the most important open question in quantum computation. What else can be done if we had a quantum computer? Of course, already this is going to be very impressive, because simulating quantum systems will enable us to study physical systems in a much more powerful way, probably design drugs and chemistry and materials. So this is going to be extremely helpful. But climate. Thank you. The most important thing. Batteries. Okay. So now what's the challenge? Why aren't we seeing quantum computers already, in our quantum laptops? So already very early on, right, immediately after Shor came up with his algorithm, the problem also became immediately clear. What happens if instead of ideal evolution, we will have problems, we will have noise, we will have inaccuracies in the evolution? The problem of noise. So I want to explain the problem of noise, because this is why we don't yet have quantum algorithms and quantum computers, and this is where most of the effort of the scientific community is put nowadays, in order to solve this problem and realize quantum computers despite this issue. So what do I mean by noise? Think of this quantum circuit. Now it's going to the right. Sorry. Before it went up. So time is that way. And these are the quantum gates. And think of a situation in which between every 2 time steps, every 2 layers of gates, you have some situation in which each qubit undergoes a little bit of a rotation in an unknown direction. For example, this state of the qubit, maybe it was supposed to be here, but something happened and it now is rotated one degree to the right. And I don't know that. Now, if I apply a quantum algorithm whose ideal result, I'm missing a line here. The ideal behavior of say, a simulation of some physical system, the magnetization would have been constant 1 in the ideal case. Well, if you have an error like that with slight rotation every time step, the result would decay. The outcome would decay, or the measured magnetization would decay, and it would become just close to 0 eventually, and very far from the ideal. And so this would happen pretty quickly, because it will accumulate fast. At the beginning, it will not have any effect, but quickly it will accumulate. And so already with algorithms which are on, say, 20 qubits or 20 gates or a few tens of gates, the result becomes useless and you can't use it. And this problem is very, very severe. Everybody's worried about it. All the major companies like IBM and Google and every startup that builds quantum computers attempts to solve this problem. Okay, now we have known already since 96 that we can solve this problem. I was luckily involved in this story, but really the main discovery is the discovery of quantum error correction. This is one of the most, if I am to say one beautiful discovery that quantum computation brought to the world, it's this discovery of quantum error correction. Why is it so beautiful? Well, what is quantum error correction? It's the ability to take the state of a quantum bit and smear it on many more qubits. Here, I don't know, hundreds of qubits set on this torus. This is just an example. Such that the quantum information is, instead of being local, it's global. So it's hidden in the entanglement between the different qubits in this torus. And why do we want to hide it in this? I'm using sort of an oxymoron. I'm hiding something by smearing it to make it larger. And the reason I'm hiding it by smearing it is because what causes the noise are local operations like the environment, like photons, for example, hitting qubits. And once they hit it, they sort of measure it and they sort of learn something about it. And quantum mechanics tells us that if the photon will learn something about it, then that information is going to be lost from the system. So if we want to protect the quantum information from losing its information to the environment, like photons hitting it, we have to make it inaccessible to these local disturbances. So we hide it by making it global. And that's the idea here of hiding the information by these local properties of whether we can actually rotate around this torus, or whether this the information is whether there is a cycle that goes around this torus or it's just local. But if you just look locally, you cannot distinguish between this cycle and this cycle. So this is the idea of multipartite entanglement in order to protect quantum states. And it turns out that if you take this idea and perform quantum computation on encoded states that are encoded using these quantum error correcting codes, you arrive at what's called the fault tolerance theorem, which is the following statement: that if the error rate, the probability for a qubit to sort of flip, like I said before, not flip, rotate by say 1 degree, or maybe the size of the rotation, the 1 degree, if that error rate is below a certain threshold, constant number, say 10 to the minus 3, then quantum computers can be made robust to noise. Then the noise will not affect it. Okay? And so this threshold theorem that says that if we manage to reduce the level of noise to below a certain threshold, we are fine. This is something that basically gives hope to the community that we can actually build quantum computers, because we just have to reduce the noise below that threshold, and then we will be able to correct errors and make those quantum algorithms work. And notice that this is a very interesting picture from the point of view of physics, because what it basically says is that if you make the noise below a certain threshold, then the physical system behaves completely differently. Just like we have cooled down the water until it becomes ice. And this different phase of matter is a phase of matter which can actually cause interactions or allows quantum entanglement in a global scale. And if we're above this phase transition, we are in this water phase where this quantum entanglement does not exist in a global scale. So what this fault tolerance theorem basically says is that if we have sufficiently many qubits, we will be able to go down below this phase transition and arrive at a new phase of matter in which global entanglement exists and is also possible to manipulate in order to generate these quantum algorithms. And so right now, this is essentially the holy grail of the community, of the industry, attempting to build quantum computers, to arrive at a situation in which we have sufficiently many qubits with sufficiently low error rates so that we can realize quantum algorithms using these protocols of error correction and fault tolerance. Okay? Okay, so why don't we have quantum algorithms if we have this result already for, I don't know, close to 30 years already? Well, the reason is that it's very difficult to do what I just said. It's very difficult to take the noise below that threshold, and it requires many more qubits. As you can see here, one qubit is encoded here using many, many qubits. And right now we are not there yet. We are just with a few hundreds of qubits. So in order to get to quantum algorithms, we would need essentially a few hundreds of thousands or more to start seeing something interesting. Okay, so I want to wrap up just by basically saying where we are going with this. So I've been a bit pessimistic about the fact that it's so difficult to generate the conditions for these quantum algorithms. So things are not as optimistic, because though the number of qubits grows very steadily, and the infidelity also improves, still the growth in the number of good qubits with infidelity is sort of the noise rate. It's not very it's not growing very fast. You see, predictions by IBM, for example, is that by 2030 we will be at 100,000 qubits, which will enable, if we think of one qubit encoded by 1,000 qubits, it will enable me to do quantum algorithms on 100 quantum bits. 100 quantum bits is nice, but it's not what we are hoping for. So things are slow. Okay, so we should expect a gradual transition to this fault-tolerant era rather than an abrupt transition. But maybe I'll skip this. But maybe I will just end with a slightly more optimistic note, which is, though quantum error correction is really the holy grail, and I think everyone agrees on that, there's probably going to be something that accelerates the path towards that holy grail, or towards that goal. And this is called error mitigation. Error mitigation is an alternative way to reduce the errors in a quantum system, and it doesn't require the huge overheads that I was talking about before. This is something that we do in my company, QEDMA, and also in other companies. There's a lot of work now on these error mitigations, and I won't go into the exact protocols because it's too technical here. But let me just say that essentially, it's not a free lunch. It's not that you give up the overhead and number of qubits and that's it. The price is that it costs much more time. Instead of one circuit, you have to apply many circuits. In fact, exponentially many circuits, but with a mild exponent. So this is it's not something that will since it's exponential, it's not something that will solve all our problems, but it will make things better. And here's an example of an experiment that we did at QEDMA, where we actually applied error mitigation and derived again the exact results instead of this decay of the magnetization that I showed you before. And these exact results are derived by applying several circuits instead of one, and then performing some classical post-processing to sort of reconstruct the correct result. Let me skip this explanation, but just say that we've recently demonstrated the largest volumes with this error mitigation that was done up until today. And these volumes, these number of gates that we demonstrated is still very, very modest. But if you take our algorithm or experiments and look at how it would work on better computers, this experiment was done on computers with a noise rate corresponding to 1.5%. But if you look at how it works on much better computers, which are very, very, which are really right around the corner, then it looks that already with the algorithms that we have today, we will be able to implement circuits with 5,000 CNOT gates. Okay, these are already circuits that are that correspond to quantum advantage, meaning circuits that cannot be simulated efficiently by classical computers. So this is very optimistic. It's not going to get us to those applications that I talked about earlier, climate, etc. But the interesting thing is, and this is something that we've realized only recently, it's likely that we will be able to combine error correction and error mitigation, and by that get rid of the overheads, huge overheads of error correction, or at least reduce them significantly. And using this combination of error correction and error mitigation, the hope is that we will have a gradual transition to those applications that we talked about earlier, a continuous path towards full-fledged quantum computation, rather than just waiting until we manage to get to full-fledged fault tolerance. Okay, so to end, let me just say that that to me this is really a beautiful example of a conversation between two fields which seemed completely unrelated, or at least not very strongly related, and it has been a very, very fruitful interaction between these two fields of computer science and physics so far, and I believe it basically changed so strongly the two fields that it's hard now to separate parts of them now, and these. The inspiration that at least I got, but many people got from the different insights that flew between these two fields were really very profound, and I think it all came from a very simple question, which has been the sort of the lighthouse of this field, which is, what is the computational power of physics? Thank you.
Thank you very much, Dorit, for this great talk. And so we have time for a couple of questions. So who is the first?
Question is, in qubits, obviously it has got lots of error, but in future, I also heard that there's a story behind that the Q date, that means not only the two state, but might be much more than two state. Then this error rate will be even more exponentially increase. Do you have any inputs regarding that, how we can mitigate, or any solutions regarding those implementation?
Yeah, so qubits are, you can actually construct everything that I talked about. You can model everything with qubits, meaning qubits with more than two states, but it won't change fundamentally the picture, because really the jump between classical to quantum started when we moved to qubits. And now when we move to qubits, you will get maybe a polynomial gain, but not an extra exponent. Okay? So sometimes you will get an important gain. It might be easier to perform various gates, etc., but it won't change the fact that qubits and qubits are polynomially related.
What technology is your current quantum computers? Is it some kind of atom that is excited or not? Or is there some, how are they done in practice? Thank you.
So the truth is that there are many different technologies that are being used. Where is that? I thought it was more towards the end. I don't know where it was. Okay. Yeah. So there are various suggestions for how to realize a quantum computer, and so, for example, I put here the 4 technologies that I think are the leading technologies nowadays, and they're very different one from another, and it's not clear which one will win. Some of them have a better, for example, error rates, meaning smaller error rates, but then it's harder to actually create interactions and control. And some of them actually are better in the sense of the fact that each qubit can interact with each other qubit. But each one of these technologies have their advantages and disadvantages. So I don't think we know at this point which one will win.
Can you please explain how those 4 technologies work?
The short answer is no. I can't. I don't think I'll dive into this detail. I mean, it's something. So optical quantum computers, for example, work on photons, and they use essentially the qubit is a photon whose polarization is the state of the qubit, and then you use beam splitters in order to create interactions. But let me note, I don't think it will be very useful if I just go through the different ones, because that's not my expertise, and B, because I think it will be too technical.
Okay, so maybe last question.
Yeah. I know it wasn't here, but okay. So there are many applications. First of all, I think you asked what would be the first one? Yeah. So first of all, in my opinion, as I said, I think the first thing to happen is that quantum simulations of systems that were not possible to simulate before will appear, and those are going to be systems that are of the geometry of the physical implementations of the quantum devices, of the quantum computers. Because once you need to use different geometries, then you need to sort of what's called transpile, or change the geometry of the quantum circuit and embed it on the right geometry of the system. And that's a big headache, and it creates a huge overhead. But if you just try to simulate physical systems of the same geometries as the quantum devices, then you very quickly see a lot of gain. And this is an application. This is something that can be done with many applications. If you can simulate Hamiltonians, or if you can simulate physical systems, you can, for example, study dynamics of chemical reactions, and study, for example, design batteries. So in my opinion, batteries and material design is probably going to be the first thing that we are going to see. Now about AI, this is a very big open question, whether quantum machine learning basically is something that is going to show as an important application or not. It has been an open question for a long time whether there are strong applications of quantum machine learning, and every time people come with a possible killer application, and in my opinion, until we have quantum computers to play with, we will not know the answer exactly, because these are heuristic problems, and just like classical algorithms, in order to design quantum algorithms, we will need something to work with, and we'll need to experiment with it and see which algorithms work. And I think that this will have to wait until, it's not going to be too long until we get to situations where we have hundreds of qubits that we can actually apply generic quantum circuits on and then play and understand what are the capabilities of these heuristic algorithms.
Okay, so with that we conclude our session. So stay tuned for the next distinguished lecture that will take place maybe in a month or a couple of months. And let's finish that with giving a big applause to Dorit for this very
Thank you.